Hello and welcome to another season of Black Hole Battles game development here on Let's Code Physics. I'm going to try a little bit different approach this season with Black Hole Battles, where I do most of the programming and debugging work off camera and then show you what I've developed. This will hopefully keep the videos closer to about 20 minutes rather than going upwards of an hour like I did last season. So I ended last season by going over different possible behaviors for our enemy ship. And it worked out fine. It was a little bit clunky. The ship died a little too frequently. It was a little bit difficult to chase, and not in a challenging way, just more in an annoying way. And since I've been learning a little bit of control theory in my self-driving car simulator, I decided to give our enemy ship an overhaul using some control theory, and I wanted to show you today the two pieces of that I've got so far. So here we are in the enemy controls subroutine. I've given it, I've appended CT onto it, so I know that this is the control theory version. I haven't yet implemented it yet because it's not complete. But what I've done is I've kept the same logic that I had before about checking for the different behaviors, as far as whether it needs to head back to the cluster, try to go between two black holes, go toward the next nearest black hole, or avoid the nearest black hole. And what I've changed about it is, instead of it immediately calling the behavior pattern there, it's setting this thing called goal point. So goal point is going to be basically the point in the game space where the ship is going to try to head. That's, it's not going to head there immediately, but that's its goal over the course of the next, series of frames. So if it's trying to return to the cluster, its goal is to head toward the cluster center of mass. So I've added in up above here a calculation of the cluster's center of mass. So basically I add to this each black hole's position times its mass, and then I divide by the total mass, and that gives you sort of the average center of mass of the black hole cluster, which is a good place for it to head toward if it's well outside. Previously it was heading toward the next nearest black hole, and that kind of just led it to just circle the cluster, which is arguably the safest thing to do, but not the best thing as far as playable combat. Going between black holes, the goal point becomes the average position of the closest black hole and the next closest black hole. Going toward the nearest black hole, the goal point is the next closest black hole. Obviously, you don't want it to land in the black hole, so that will probably require some adjustments depending on how the trajectories shape out. And then, of course, if we're trying to avoid the nearest black hole, then the best thing to do, I feel like, is take the ship's current position and subtract off the relative position vector. So in other words, if the black hole is over here and the ship is here, it's going to head in this direction. So that's pretty straightforward. The next thing that we have to do in a control theory subroutine is generate the possible trajectories toward the goal. So you have the starting point where the ship is, you have the ending point. Actually, let me draw this. That would be even better, isn't it? Rather than me gesturing with the mouse. Here we go. So if you imagine if the ship is here and the goal point is over here, then you could have several trajectories going there. You could have a pretty straightforward trajectory heading that way. You could have a sharper trajectory heading that way. You could have a sharper trajectory that goes over to the other side. But it's also important to consider you might not necessarily be heading for that point exactly. You might be happy with that point, or a point nearby, or a point near that, or a point near that, or a point near that. And so what the goal is to generate several goal points, several possible acceptable endpoints, and then you generate two trajectories to each one. You generate a smooth, I did not start drawing that smooth, you generate a smooth trajectory toward each one, so there's a nice smooth trajectory, and you generate a sharp trajectory toward each one. So the difference between those two is that the smooth trajectory, this one in the middle here, maintains the same initial curvature as your current trajectory. So the ship, if it's moving, which it usually is, has a current trajectory that it's heading on, and so a smooth trajectory maintains that initial curvature, the t squared term in the polynomial, if you will. Or you can have a sudden change to it at the beginning and get a sharp trajectory. And so for each one of these points, you can get two trajectories. You can get a smooth trajectory and you can get a sharp trajectory. So if you've got 5 possible goal points and 2 trajectories on each, that's 10 trajectories. That's pretty good options, because you imagine, going from your sharp trajectory over here all the way to your sharp trajectory to this endpoint. Gives you a pretty wide range. I mean, you could fit a black hole inside there, and basically then you select the best trajectory that keeps you away from the black hole or away from the enemy ship or from the player ship. And so that's what I've got in this chunk of code. We have to establish what the starting point is. We've already gotten what the end point is. And so what we do here is we start calling a subroutine called makeTraj for make trajectory. And that requires several arguments. So it's going to require the starting point, so that's where the ship currently is. It requires the goal point, and the goal point can be adjusted based on how far over to either side you're willing to go. So that's being adjusted by this variable lat distance for lateral distance. So if we go back to our diagram here, each one of these is separated by lat distance. So this is a lat distance, this is lat distance, this is lat distance, this is lat distance. And we're basically taking that in a direction that's perpendicular to the vector between the ship and the goal point, the original goal point. And you notice I'm calling makeTraj twice here, once for it going in the positive direction and once for it going in the negative direction. So for each time around the loop, we get 2 possible trajectories based on the 2 endpoints that are symmetric across the goal point. And so I also have to tell it what my current velocity is in the x direction and in the y direction. I have to tell it what my current acceleration is in the x direction and y direction, because that's the slope of the trajectory, or at least the initial slope of the trajectory, and the initial curvature of the trajectory. So for a smooth trajectory, I just keep this initial curvature the same. For a sharp trajectory, down here in the second loop where I'm generating these sharp trajectories, I'm going to change the initial acceleration, the initial curvature, by a little bit, by an accel bump. So this will be something like 1.1, 1.2, something like that. Again, so that way we can get that sharp trajectory. And then of course I have to tell it the lateral distance, and positive will mean in one direction, negative will mean in another direction. So I've got that make trajectory subroutine down here. Here's all the inputs that it takes. Again, it takes a starting point, the goal point, the x velocity, the y velocity, the x acceleration, the y acceleration, and the lateral distance that we want to travel. So this thing is going to have, this is going to return a list of 4 points, because if you want to have a let's see, this is a cubic fit, because we've already got the first power fixed and the second power fixed. So our degree of freedom is in the third power. And so let me bring over here the math that I've done for this. So all these coefficients are already fixed. So if you want to take this out to the third power, we've got to have 1, 2, 3, 4 coefficients. One that's a constant, one multiplying t, one multiplying t squared, one multiplying t cubed. And 3 of those are already fixed. So the 0 coefficient is just the initial position. That's the starting point. The first coefficient, the 1 coefficient, is the initial velocity. The second coefficient is the initial acceleration. And so what we can get out of that is we can solve for the third one. I forgot to denote that with a 3. My bad. Yes, yeah. Sorry, was doing a little bit of calculus in my head to make sure I had that right. Yes, I do. So this is going to be... Oh, actually, that's not the acceleration, is it? That's half the acceleration. Right, I need to multiply this, because if I take a derivative of this, acceleration is going to be 2 times that, so this is actually half the acceleration. My bad. I knew I was missing something, so this is going to be half the acceleration. Okay, so I do need to make a correction there. And so this is actually not going to be the jerk. This is going to be the... let's see. No, actually, this is fine. I can solve it for that. I need to make a correction to these accelerations, though. Excuse me 1 second. Where did that go? Here we are. Okay, so I need to make a change to this, where this is... let's see. This needs to be 1/2 the acceleration. I suppose the easiest thing to do is to just take... Let's see. Yeah, because this needs to be 1/2 the acceleration. Let's just take XL and multiply it by 1/2. And do the same with YXL. Because when you take the derivative, it's going to drop that 2 power down, and so we have to account for that. So that's fine. And this actually is not the jerk. This is 1/6 of the jerk. But we won't worry about that just for the sake of it's the jerk coefficient, if you will. And so basically I can take this equation and I can solve it, and basically I take my x, and this is x at the goal point, and I subtract from it all the other a's times t to the corresponding power. So I subtract from that a0, I subtract from it a1 times t, I subtract from it a2 times t squared. So all of this is what's going into that summation business. And then, of course, I need to divide everything by t cubed. That's where this comes from. And then I can do the same thing for b. I just replace the a with a b and replace the x with a y. And that's what I've got implemented over here, where we're solving for the jerk coefficient. And so what I've done, instead of multiplying by a bunch of t time powers and then dividing by a bunch of time powers, I've just gone ahead and done the cancellation there. So the x's get divided by time to the 3rd power, the velocities get divided by time squared, and the accelerations get divided by time to the 1st power. So that lets me find out what that final coefficient is. Once I have that final coefficient, I can generate my trajectory point. So I need 4 trajectory points. The first one is hopefully, obviously, going to be the starting point. So I've gone ahead and added that up here. And so then I need to add 3 more. And they're each going to be separated by a delta time, because we are working with the velocity and acceleration. So we have to scale this in terms of the time step in the program. And so what I've got here is I'm just recreating that polynomial equations. I've got the initial x plus the initial velocity times time, plus the initial acceleration times time squared, plus the jerk times time cubed. And then I do the same thing down here to get the new y, and then I add to that trajectory my new coordinate x and y. And so it's going to run that twice every time we go around the loop. Once moving the goal point to the in one direction, once moving the goal point in another direction. And then we'll run it again, getting sharp trajectories, again going in one direction and then going in the other direction. So I think I have that set up correctly. I'm going to see if I can create some graphics to show me those trajectories before I move ahead, just to make sure that I have them. Once those are working, we need to move on to the next 2 stages, where we evaluate the cost of each trajectory. This is where we check for things like proximity to a black hole, likelihood of running into the player, and so basically whichever trajectory, so we'll generate, some, like say 10 trajectories. Actually, I guess it needs to be a multiple of 4, doesn't it? So we'll generate, say, actually, I guess that doesn't matter for the first one. Yeah, no, we could generate 10 because this one would be 0 for the first one. Anyway, point being, we generate some number of trajectories. Let's say 20. Let's be generous, and let's say we generate 20 trajectories. We need to evaluate the cost of each of those trajectories, and we select the trajectory that has the lowest cost, the one that's the least risky for us, or that has the highest benefit for us. And then we have to actually execute the trajectory. So the trajectory is all well and good, but the ship can only control its rotation and its thrust. So this is where we convert the trajectory into a plan for how to change the thrust and the rotation of the ship. So that is what we will work toward next time. So thank you so much for watching. I'm glad to be back in space with you. I will see you next time. Bye-bye.